Hi all. Despite being off season for past papers and physics and all that, I decided to make another video just because I was bored. I'm sitting here having not a lot of things to do, sadly. So I decided to go over a past paper, and this is a Unit 1 paper, and it's the A version. So this is Unit 1A, and it's from October 2025, as you can see. So this is one of the most recent ones. And I think this is the first time, this October 2025 season was the first time Edexcel introduced these Unit 1A, Unit 2A, Unit 3A, etc. versions, which, as I was informed from comments that you provided under past videos I posted, these are kind of like there for in the case that a paper is leaked, so they have sort of a backup paper. But anyway, it's good practice to go over this paper. So let's start and see how this goes. Unit 1 again is mechanics and materials. So it's the first test in at the AES level, and it's 90 minutes. And as I say in most of my videos, try to spend about a minute per mark. So if the problem is 10 marks, it should take you about 10 minutes, and so on and so forth. So let's dive in, and let's start with section A, which is the multiple choice section. Question 1: which of the following is a vector quantity? So distance is not, is a scalar, okay. Speed is also a scalar, okay, but velocity is not, okay. So C is the correct answer, and the work done is also a scalar, okay. So let's move on to part 2. A cylinder of weight 1.5 newtons is placed on top of a vertical string, and the spring compresses by 3 centimeters as shown. What is the spring constant of the spring? Okay, so just two forces act on our body, so we can write them down. So the weight, okay, so the weight, and that pulls down, and then the spring pushes up by k times delta x, and we have equilibrium. So k times delta x is equal to the weight. So k is nothing but the weight over delta x. So the weight is 1.5 newtons, and delta x is 0.03 meters. Okay, 3 centimeters is 0.03 meters. So we get 50 newtons per meter, which is option D. I don't know why I'm writing with green. Let's go back to black. Which of the following SI units can only be used with a scalar quantity? Okay, meters can actually be used with a vector quantity, which is called displacement. Okay, displacement denotes both, has both a magnitude and a direction. Okay, the direction of the displacement of an object. So even though it's tempting, A is not the correct answer, and then C and D are definitely not the correct answers because that's velocity and acceleration that do have direction. So B is the right answer. Time doesn't have a direction, it's a scalar. Though it would be cool to have a direction, so it could go backwards, but we can't. So at least not in this universe. So let's move on to question number 4. A student measures the time t taken for a ball bearing to fall different measured distances s from rest. The student uses his measurements to plot a graph with a gradient equal to the acceleration due to gravity g. Which row of the table shows a graph with a gradient equal to g? Okay, so you have a ball bearing that falls in a free fall, okay, no air resistance and stuff like that. Do they specify that? They don't, but we assume that it's not there. So it starts from rest, so u is 0, and it falls by distance s, okay, and this is the vertical direction, but nevertheless we can use that equation. So s is going to be u times t plus 1/2 at squared. So in this case we have 0 initial velocity, and the object's velocity points downwards, just like the acceleration, which is g, right? So we immediately see that S is 1/2 gt squared. And if I bring 2 to the other side, we have 2s equals to gt squared. Okay, so if we plot 2s versus t squared, we will have a straight line through the origin, straight line through origin, okay, with gradient equal to g. Okay, so the correct answer is B. Okay, I hope this makes sense. Let's move on to question 5. And by the way, guys, as I say in all of my videos, if something is not clear, I'm not perfect, I make mistakes, so just point it out in the comments and I will come back to you with clarification if needed. So, two forces P and Q act on an object as shown. Which of the following is a correctly drawn scaled vector diagram for the resultant R of forces P and Q? Okay, so by the form these two forces have, the most natural thing to do is to use the parallelogram method to add vectors. And by the way, I have videos on these things. I mean, if you search my channel. So you draw a vector parallel to Q, and sorry, a dashed line parallel to Q, and another dashed line parallel to P, and the diagonal, okay, so the diagonal is P plus Q. So let's go see. Okay, so this is going to be R. So in options A and B, R points in the wrong direction, and the same goes for C. So actually the correct answer is D, but they use a different method to add these vectors, okay? So I'm gonna erase what we just did, which is the natural thing to do. And what they actually do in D is to parallel transport Q, okay? So they use, okay, so that's your Q. So you add the tail of P with the head of Q, which you parallel transport that in that fashion. So R is that vector, okay? So the parallelogram method and the method that they use here are equivalent, okay, as they should, okay? So let's move on. Okay, question 6. The path of a projectile, excuse me, is shown, okay? The projectile landed at a height lower than the height from which it was launched. Assuming there is no air resistance acting on the projectile, which of the following is a correct statement? Okay, A, at the maximum height, the horizontal velocity is a minimum. That's totally false because the horizontal velocity is constant if there is no air resistance, okay? So let's move to B. At the maximum height, the vertical velocity is a minimum. No, sorry, at the maximum height, the vertical velocity is a maximum, excuse me. So that's totally wrong because at the maximum height, the vertical velocity is 0, okay? So minimum. C, the initial velocity, horizontal velocity is equal to the final horizontal velocity. That's correct, okay? Because there are no forces acting in the x direction, okay? So if there was air resistance, that would not be the case, okay? And then D says the initial vertical velocity is equal to the final vertical velocity. No, okay? And yeah, okay. 7. The force extension graph for a wire is shown. When a force F1 is applied across the ends of the wire, an extension E1 is produced. Which of the following correctly describes the work done to extend the wire? Okay, so first of all, the force is in newtons and the extension is in meters. So if we multiply force and extension, we get units of newtons times meters, which are joules. In other words, the area under the curve, so this is E1. So this area is the work done to extend the wire, okay? So what is that area though? What is that area though? A is not correct because that's the area of a triangle. So what A is saying is that this is the area pretty much, okay? So A would have been correct if the graph looked like this red line that I drew now, okay? So that would be a triangular area. So, but it's not, okay? So B says that the area is larger than that triangular area I just mentioned, and that's correct, right? Because C and D are totally wrong, because you have the totally wrong dimensions, because they divide. So this is newtons over meters, okay? So that will not be a work. So C and D actually show a quantity that will be, I don't know, the spring constant has units of newtons per meter, not the work done. So C and D are totally wrong, okay? So B is the correct answer. Let's move on. 8. A ball is thrown vertically upwards with a velocity of 3 meters per second. Which of the following is the acceleration of the ball at its maximum height? Okay, so you throw the ball. So this is the ball, okay, moving up. And as it moves up, okay, the acceleration is in the opposite direction, okay, because so it slows it down, okay. So this will be the case even when it reaches the maximum height. So the correct answer is D, okay, because the velocity points up as it moves up until it reaches the maximum height, and the acceleration points down, okay. But when it reaches the maximum point, if they asked, okay, after it reaches the maximum point, what's the acceleration? The acceleration will have been plus in that case. But in our case, it's D. Okay, A and B are totally wrong. I don't even know why they are there as options. So let's move on to question 9. Which of the following statements is not correct for a Newton's third law pair of forces? So option A, the forces act in opposite directions. That's in fact correct. B, the forces act on the same body. Okay, that's totally wrong. Okay, actually, usually when you want to teach Newton's third law, you demonstrate the cases when it is wrong, and you usually demonstrate two equal and opposite forces acting on the same body. So those forces are not a Newton third law pair. Okay. 10. The diagram shows a roller coaster. Let me know in the comments if you have been in roller coasters. I'm sorry, it's difficult for me to pronounce it. I've been in a roller coaster in Athens, Greece, when I was really young, and I was terrified of it. Okay, and I've been to another one in Orlando, Florida. I think it was the Disney theme park or something like that. I went there with friends. I am not too much into these things, and I was again terrified. So yeah, but let me know if you like them. So okay, the roller coasters the roller coaster car stops momentarily at P before descending towards Q. Which of the following expressions could be used to determine the velocity of the roller coaster car at Q? Okay, so we can use conservation of energy between P. Okay, so we have P and Q. Okay, at P, we have a potential energy of mg times delta H. Okay, and delta H is simply 75 minus 30, right? So mg times 75 minus 30 will be equal to the potential energy there is 0, so we will have 1/2 mv squared, right? And these two guys should be equal. So we immediately see that we have v squared is equal to 150 g minus 60 g, because m cancels and we transfer, okay, these two are equal, and we transfer 2 to the other side. So v squared is 90g. So v is the square root of 90g, which is d. Okay. The other options are weird. I don't know why they are there. So let's move on to the next question. And by the way, this was the end of section A. So let's move on to section B. Okay, question 11. A uniform plank of length 4 meters is pivoted 0.9 meters from one end. The weight of the plank is 250 newtons. A person of weight 950 newtons stands at one end of the plank. A person of weight 650 newtons stands at distance x from the pivot so that the plank is in equilibrium as shown. Add to the diagram in the answer book to show the forces acting on the plank. So first of all, we have the weight of this person, so 950 newtons, the weight of the second person, so 650 newtons. Then at the center of mass, which is at 2 meters for this object, right? So somewhere there, we will have the 250 newtons, which is the weight of the plank, right, acting down. And then we also need the reaction from, we need the reaction from the pivot that points up, okay? And even though they don't ask, the reaction force should be equal to the sum of the other three forces for equilibrium, okay? Then in part B, they ask us to calculate the distance x. Okay, so the force of 950 newtons times 0.9 meters should be equal to 650. We are taking moments from the pivot, so 650 times x plus 250, and the distance from the pivot for that object, I mean from the for the 250 newtons, the weight for the weight of the plank, the distance is 2, let me see, wait, I'm confused. So 2 meters minus 0.9, right? Yes. Okay, I'm sorry. So let's solve. So we get 650x, okay, is equal to 580. So x is 0.89 meters, or about 0.9 meters, okay? So this was question 11. Let's move on. Question 12. Moving walkways are often found in airports. One moving walkway carries passengers up an incline of 30 degrees as shown. A single passenger of mass 72 kilograms stands on the walkway. The speed of the walkway is 0.51 meters per second. Show that the rate at which the walkway does work on the passenger is about 200 watts. Okay, we're gonna create a clean page and work there. So this is problem 12, okay, because there is no space. So this is the incline. So this is 30 meters. And let's model the person as a box, okay? So we have the weight pointing down, okay? And we have to analyze this weight in an axis parallel to the incline and an axis perpendicular to the incline, okay? So this angle is 30 degrees. I explained it in many of my videos, but the way to figure this out is to realize that this line is perpendicular to this line, okay? And then this line is perpendicular to this line. Okay, so this inscribed angle should be equal to that inscribed angle. Okay, so that's the way to prove it. Let me remove that mess. Okay, are we good? Okay, removed. Okay, so let's analyze the weight. So there is a component of the weight mg sine 30 parallel to the incline, and a component mg cosine 30 that we don't care about much. And also, I mean, if you want to be precise, there is also the reaction from the incline. Okay, so let's find the work done. So the work done, since we move up, it's actually minus, but we don't need it. We are not going to use it. So mg sine 30 degrees, and the minus sign comes from the fact that although we move up, the force points down, but okay, we are not going to use it. I've just put it there for completeness, times the distance covered on this ramp, okay? And the power is the work done per time, okay? So mg, now we drop the minus sign, mg sine 30 times s over t, but this is nothing more than the velocity of the walkway. So we have velocity times mg sine 30, And if we plug in the numbers that they give us, we find 180.1 watts, which is kind of close to the 200 watts that they state. Okay. Part B, the walkway system has an efficiency of 78%. Calculate the power input to the system when 15 passengers of average mass, 72 kilograms, are standing on the walkway. Okay, so that's B. Okay, so the efficiency is the useful power over the input power. Okay, so the input power is going to be equal to the useful power over efficiency. What do we mean by useful in this case? It's the 15 persons times 180.1 watts, right? That's the power we get out of this, okay? Over the efficiency of 0.78. Okay, so what goes in is actually 3,463.5 watts, which is the input power, okay? So that's the answer. We can move on to the next question. I think there is nothing more to add here. Okay, 13. Stokes' law can be used to determine the magnitude of the viscous drag for small spherical objects moving through a fluid. State one other condition that must be met in order for Stokes' law to apply to the moving object. So I'm going to start another clean page to answer this first question. So for part A, we need low speeds, laminar flow, and no turbulence to apply Stokes' law. Okay. B, a sphere falls through water at a constant speed of 0.5 meters per second. Assess whether Stokes' law can be applied to the falling sphere. You should include calculations in your answer. They give us the diameter of the sphere, the mass of the sphere, the upthrust on the sphere, and the viscosity of water. Okay, so for part B, if we have a sphere falling through the water, we will have the weight acting on it, the drag force, and the upthrust. Okay, so the weight is mass times g. So 9.1 times 10 to the negative 4 times 9.81, and this is kilograms meters per second squared. Okay, so all these things are given. I mean, that's the mass of the sphere. So we can find the weight as 8.93 times 10 to the negative 4 newtons. Now, the drag plus the upthrust are equal to 1.1 times 10 to the negative 3, that's newtons, plus 6 pi eta, the viscosity, rho, the radius of the sphere, times v. And if we plug in the numbers, we find 1.1 times 10 to the negative 3 from before, plus 6 pi times 8.9 times 10 to the negative 4 times 3 times 10 to the negative 3 times 0.5. And what we find is 1.13 times 10 to the negative 3 newtons. So the weight is actually not equal to the drag plus upthrust. So the statement is wrong, okay? So what does the statement say? Assess whether Stokes' law can be applied to the falling sphere. So no is the answer, okay? Okay, so this was question 13. Let's move on to the next question. Okay, question 14. A teacher demonstrated the motion of a small sphere falling through a vacuum and through oil. The teacher used a motion sensor and data logger connected to a computer. The computer plotted graphs of velocity against time for the sphere are shown. Okay, so we have the velocity versus time for the oil and the vacuum, okay? And by the way, this is an extended answer, a long writing answer. So this, because of the asterisk, I mean. So these questions usually are worth 6 marks, and you have to provide about 5 to 7 sentences to describe them. So anyway, explain the differences between the shapes of the graphs. So let's go to the back. So in the vacuum, okay, in the vacuum there is no air resistance, okay. So the weight is the only force, and it's a constant force, okay. Now, constant force means constant acceleration, right? Because of F equal to ma, okay. So for vacuum we see a straight line, okay, with gradient equal to a, okay, equal to g probably, because this is a free fall, okay. So this is why we see this straight line, because we get from the gradient we get the acceleration, okay. I don't know why I did this, but you get the idea, okay. You find the gradient of this line, you get the acceleration, okay. Now for oil, in oil, okay, the sphere starts slow, okay, so the drag is small, okay. And remember that in the Stokes force case, so Fs is the Stokes force, okay, the force is proportional to the velocity, okay. So the sphere starts slow, so the drag is small, okay, but as velocity increases, the force, the Stokes force, increases, okay. Um, we can also call it drag, so we can also call it d, okay. D and Stokes force are the same thing, okay. Now as the Stokes force, the drag, increases, the sum of all forces, okay, the resultant force is going to be the weight minus the drag minus the upthrust. And we know this because if we have a ball bearing falling in a liquid, we will have, of course, its weight and then the drag and then the upthrust, okay. So the sum of all forces is going to be the weight minus the drag minus the upthrust, because the object is moving down, so the weight counts as positive, okay. So as the Stokes force, by the way, drag and Fs are the same. I'm sorry, I'm using them interchangeably. So as the Stokes force increases, the sum of all forces, oops, I don't know why I did this. So the sum of all forces decreases. So the acceleration, which is the sum of all forces over m, decreases and gets smaller and smaller, okay. Okay, eventually the weight becomes equal to the drag plus the upthrust, so the sum of all forces is 0, so the acceleration is 0, so we reach terminal velocity, okay, and the graph becomes horizontal, denoting that the acceleration is 0 pretty much, okay. And that's the answer. I hope it's clear, but you can see that we get a straight line, which means that we reach a terminal velocity and there is no more acceleration acting on the ball. Okay, this was question 14. Let's move on. Okay, question 15. A student carried out an experiment to determine the Young modulus of copper. She added a mass m to the free end of a sample of copper in the form of a long thin wire, and the corresponding extension delta x was measured. This was replaced for increasing masses. Okay, question A, state the meaning of the term Young modulus. Okay, let's create a clean page so we have space to write. So the Young's modulus E tells you how stiff, okay, a material is and how much it resists stretching. Okay, it is defined as stress over strain, but it only applies to the linear region. What I mean by that is that if you remember the stress versus strain graphs, they start out straight and then they become something else, okay. So the Young modulus is only defined in the straight region that I circled there with red. Okay. B. The student repeated the measurement of the diameter of the wire at different positions and orientations of the wire. She obtained the following results. So we have 4 diameters there. Question A, determine the cross-sectional area of the sample of wire used. Okay, so this is B part A. So the average diameter, first of all, is the sum of all the measurements, 0.235 plus 0.230 plus 0.240 over 4. Okay, so that's 0.234 meters. So the area, cross-sectional area, I'm sorry, is pi d squared over 4. So we find 4.29 times 10 to the negative 8 meters squared. Okay. 2. The student plotted a graph of m against delta x. She measured the gradient and obtained a value of 195 kilograms per meter. Determine the Young modulus of the copper, and they give you the length of the sample of copper used as 3.5 meters. Okay, we need a little bit of work for this one. So we will start from stress equal to strain times the Young's modulus, okay? But the stress is force per cross-sectional area. The strain is equal to the extension over the total length times the Young's modulus, okay? But now the force was the weight used, so m times g over a is equal to delta x over L times the Young modulus, okay? So let's rearrange this. So the mass is equal to the Young modulus times the cross-sectional area over g times the length of the wire times delta x. Okay, so they plotted the mass versus delta x, which is going to be a straight line through the origin with gradient equal to the Young modulus times the cross-sectional area times g times L. So E, the Young modulus, which we care about, is going to be the gradient times g times the length over the cross-sectional area. So let's plug in. We have 195. Actually, let me use a clean line. So 195 is the gradient, and I will put the units all the way to the right, so kilograms per meter, and then g is 9.81 meters per second squared. The length is 3.5, that's meters, and then we have to divide by 4.3 times 10 to the negative 8 meters squared. So this unit over here is the Newton, okay? We can cancel these meters, and then newtons over meter squared is pascals. So the final value is 1.56 times 10 to the 11 pascals. Okay, that's the answer. Part 3, the experiment was repeated by another student using a 2-meter length of the copper wire. Suggest how the values obtained for the gradient and hence the Young modulus will differ between the students. Okay, so we will start with this equation. So let's use a clean page. So shorter, so this part 3. So shorter wires, excuse me, stretch less for the same force. Okay, and we can see this from this equation. So delta x is proportional to the force and to L. Okay, so if we actually take, let me show you actually. So if we take this one, can we copy it? Actually, yes, we can. Let me select it. And where is the copy? Okay, copy. And let's do, sorry about that. Okay, paste. So let's move it there. Okay, so if we solve for delta x, we have that delta x is equal to force times length over cross-sectional area times over the Young modulus, okay? So delta x is proportional to the length, okay? So shorter wires stretch less for the same force, okay? So if delta x is smaller, okay, the gradient, which is m over delta x, is larger actually, right? Because delta x gets smaller, okay? So the gradient increases for the second student. Let me see, is there another way to see this? No, I mean, if delta x, m over delta x is actually proportional to 1 over L. And again, that's another way to see it. I mean, if L gets smaller, I mean, if you take it, if you take this equation again, so m over delta x is equal to A times E over, I'm confused. Yeah, G times L. So if L decreases, m over delta x increases, okay? And that happens to be the gradient, okay? But E, the Young's modulus, is the same for both students, as E is a property of the material, okay? And not the shape or length or cross-sectional area or anything, okay? So that's the trick there. So the Young modulus will be the same, okay? Let's move on to the next question. Okay, 16. The photograph shows a fireboat used to put out fires on ships at sea. A pump fixed to the boat pumps water from the sea. The seawater is projected at high speed out of a pipe connected to the pump. Question A. The mass of water pumped each second is 300 kilograms. The pipe has a radius of 5 centimeters. The density of water is 1,300 kilograms per cubic meter. Show that the speed at which the seawater is projected from the pipe is about 37 meters per second. So as usual, let's move to the back. So this is 16 part A. Okay, so first of all, let's find the volume per second ejected from this pump. So the density of seawater is mass over volume. So volume is mass over density, right? But they actually give us, I mean, if we divide, so volume per time is equal to mass per time times 1 over rho, okay? I mean, we can do that because we can delete t and then recover the original expression, okay? And actually mass per time is what they provide for us. So the volume per time that is pumped out of this pump, okay, out of this pipe, okay, is mass per time. So 300 kilograms per second, this is what they say, over 1,300 kilograms per cubic centimeter. So kilograms drop out, and we find that the volume of water per time is equal to 0.291 cubic meters per second. Okay, now let's find the cross-sectional area of the pipe. So the cross-sectional area is pi r squared. So pi times 0.05 squared meter squared. So we find 2.85 times 10 to the negative 3 squared meters. Now, the volume per time ejected from the pipe should be equal to this cross-sectional area, right, times the velocity of the water as it comes out. Notice that the units for the left-hand side are cubic meters per second, and for the right-hand side is meters squared times meters per second, which is also cubic meters per second. Okay, so this is the equation we need to use pretty much. So you have to kind of invent this, is my guess. in this paper, but it kind of makes sense. I mean, the volume of water per time coming out of the pipe should be equal to the cross-sectional area, right? I mean, if you imagine it, so you have something coming out, so the distance it covers per second is the velocity, of course, times how many of these particles come out. They are going to be equal to the area of the pipe, okay? So this is what we need to use. And let me see. So velocity is volume per time divided by the cross-sectional area, and this gives us 32.1 meters per second. Let me check my calculations again. Sorry, 37 is the answer. I don't know why I wrote 32. So 37.1. Okay, so yeah, that's the answer. Let's move on to part B. Projecting water from the pipe causes a force to be exerted on the pump. Explain the direction of the force on the pump. Okay, let's create another clean page. Okay, so the pump, okay, pushes water forwards, okay, out of the pipe, okay. By Newton's third law, the water must push back on the pump, so must push back on the pump, okay, with an equal and opposite force. Okay, so the reaction force acts backwards. And that's the answer. Okay. C. Initially, the pump is turned off and the fireboat moves forwards through the water at a constant speed. The boat's engine provides a constant forward force. When the pump is turned on, water is projected forwards and the fireboat slows to a lower constant speed. Explain why the boat now has a lower constant speed. Okay, so part C. So turning on the pump, okay, introduces a backward force on the boat. Okay. This backward force is the force that we discussed about in part B, pretty much. I mean, the Newton third pair. Okay. So now we have so sigma F decreases pretty much. The sum of all forces decreases. Okay, and the boat decelerates. Okay, and the sum of all forces decreases because we introduce another force backwards. Okay, so eventually the force from the engine will become equal to the drag again plus this reaction backward force. So the boat will stop decelerating and start moving at a lower constant speed. Okay, so that's the answer because we introduce another force into this mix. Okay, let's move on to the next question. Okay, 17, and distress flare may be launched from a boat to signal for help. A flare was launched from a stationary boat at an angle of 30 degrees to the horizontal. Part I, the flare was launched to the right from the launch position marked X on the boat in the diagram below. Complete the diagram to show the path taken by the flare before it hit the sea. So it's gonna be something like this, I guess. Okay, parabola, I mean, because this motion in the gravitational field of the Earth. Okay. 2. The maximum height of the flare above the launch position was 42 meters. So this distance, I guess, so 42 meters, show that the flare was launched at a speed of about 60 meters per second. Okay, so let's draw a few vectors here. So first of all, that's the velocity of of the flare, right? Okay, and it can be analyzed into a horizontal component. Ux is u, and then cosine of 30 degrees, okay, because they tell us that that's 30 degrees. And then another component, the vertical component, uy, is going to be u times sine of 30 degrees. Okay, now let's use a clean page to finish this problem. So this is part 2, right? So we can use Suvad equations to find, okay, in the y direction, okay, we start with this uy component, which is equal to u sine 30, and the y component of the velocity becomes 0 at the maximum point. Okay, so we will exploit that, meaning that vy squared, okay, we can use the Suvad equations. So vy squared is going to be equal to uy squared plus 2a times the distance covered. So in our case, the final velocity in the y direction at the maximum point is 0, and this should equal to uy squared minus 2g times h max. I hope this makes sense. The reason why we need a minus sign is that, okay, first of all, it wouldn't make sense because we will have a negative velocity squared. And then if we take the square root of that, it will be an imaginary velocity, which doesn't make sense. But anyway, the reason is because as the vertical component of the velocity points up, the acceleration points in the opposite direction. That's why we need the minus sign. Okay, so if we solve for Vy, this is going to be the square root of 2 times 9.81 times 42. So that's 28.7 meters per second. Okay, but Uy is U sine 30 degrees, right? So U, the launch velocity, is Uy over sine 30 degrees, which is 57.41 meters per second. Do they specify anything? Yeah, they say about 60 meters per second, so we're close. Okay. Part 3, the flare was visible from a maximum distance of 8 kilometers. A rescue boat was 8.2 kilometers from the boat in distress. Determine whether the flare traveled a sufficient distance to be visible from the rescue boat. You should assume that the flare was launched in the direction of the rescue boat. Okay, so basically there is a 200 meters difference between the flare being visible and the rescue boat. So does it make it past that? Let's see. So in other words, you have to find the time of flight and use the time of flight to calculate the maximum distance covered in the x direction. I hope this makes sense. So you have to find this pretty much. So we have to find Sx. Okay, and finding Sx is simple, kind of, because S is u times t plus 1/2 at squared, but in the x direction there is no acceleration. So Sx is Vx times t, okay? And Vx is u times cos 30 times t. But we don't know t, but we can find t. How? We will use the vertical, we will exploit the fact that the vertical velocity becomes 0 at the top again. So Vy is uy plus at, okay? But uy at the top is 0, uy is, we calculated it, so I'm just gonna write it as uy, minus g times t. Okay, so t is uy over g, or 2.925 seconds. Okay, but that's the time to go up. It will need another 2.925 seconds to go down. Okay, so let's use another clean page. So the time of flight is 2 times the time needed to go up. So that's 5.80 85 seconds, I think. Yeah, that's the answer. Okay, so S is U cosine of 30 times of light. So this gives you 290.5 meters if you multiply everything, which is larger than 200 meters. So yes, they will be rescued. They are lucky. Okay, so that's problem 17. And let's move on to the next one. Okay, question 18. A game is played where each player must use a mallet. Is that the correct pronunciation? To hit a disc across a table into the opponent's goal. One player accidentally lets go of a mallet. The mallet travels at a speed of 1.6 meters per second and collides with a stationary disc. After the collision, the mallet continues in the same direction at a lower speed of 0.3 meters per second. The disc moves in the same direction as the mallet with a velocity v as shown. Okay. Question A, calculate the value for V. Assume that frictional forces are negligible, and they give you the mass of the disk and the mass of the mallet. Okay, so we have the before the collision, the after the collision situation. So let's use a clean page. We have the mass of the mallet times the velocity of the mallet. Actually, let's use U because it's the initial velocity. So U of the mallet, okay, is equal to the momentum after, right? So that's going to be the mass of the mallet times the velocity of the mallet after the collision plus the mass of the disk times the velocity of the disk, right? So we can solve for the velocity of the disk to find this is going to be equal to the mass of the mallet times the initial velocity minus the final velocity for the mallet over the mass of the disk. And if we plug in numbers, we find 6.3 meters per second. Okay, this was part A. Part B, to reach the goal, the disk must move up a ramp, which is at an angle of 30 degrees to the horizontal. The velocity of the disk at the bottom of the ramp is 5 meters per second. The disk moves up the ramp, and work is done by the disk against the frictional force. The disk moves a distance of 6.5 centimeters up the ramp before moving back down, so it stops. Okay, determine the frictional force acting on the disk, and they give you the mass of the disk. Okay, the way I thought about it, maybe there's a better way to explain it, but I thought about it as follows. So this is the distance up the ramp. The disk covers the 6.5 centimeters. Okay, therefore it makes it up to a height h, right? Which we can calculate since h is going to be nothing but 6.5 times sine of 30 degrees or 3.25 centimeters. Okay, and we can use conservation of energy in a funny way, let's say, because this is not something you use very usually, but how can you apply the conservation of energy here? So when the disk is moving down here, it has a kinetic energy 1/2 mv squared, right? And when it makes it at the top, at the point where I marked with a cross, it will have a potential energy mgh, right? But some work will be done by the friction while it moves at the ramp. So the work done by friction is going to be equal to the frictional force times the distance s up the ramp, and s is just 6.5 centimeters. Okay, so in other words, the conservation of energy will give you something funny. So let's do B. So the kinetic energy that the mallet has before it reaches the ramp will turn into the potential energy, right? Plus the frictional force times the distance, which give you the work done by the friction. Okay, so the friction is going to be 1/2 mv squared minus mgh over the distance s. Okay, so this is going to be equal to 0.5 times the mass of the mallet, 0.035, times 25, which is the velocity squared, minus 0.035 times 9.81 times 0.030. Wait, let me see. 35. Oops. No, that's the height. Sorry, the height is okay. So 325. Excuse me. Over 0.065. Anyway, the answer is 6.56 newtons, which agrees with the Mark scheme. They do something different in the Mark scheme, but to me, it makes more sense to solve it this way, using conservation of energy. Okay, you don't usually think of conservation of energy when you hear friction, but hey, friction does work, right? And that work is going to be consumed by whatever energy is available. So the only available source of energy is the kinetic energy. Part of it is going to be eaten, if that makes sense, from the frictional force, and another part from the potential energy, and that's the problem. That's the answer. Okay, let's move on to the last question, 19. Okay, a student used the apparatus shown to investigate the forces acting on a uniform solid sphere placed in water. Draw a free body diagram for the sphere when it is suspended in water as shown in the answer book. Okay, so we will have the weight of the sphere pointing down. It's not visible. Let's use red. Okay, the weight of the sphere, the wait, what am I doing? There is no drag force. It's not moving. I'm sorry. The upthrust is the other force, and then the tension from the string. Okay, so these are the forces. Okay, B. As the sphere was lowered into the water, the reading on the balance increased from 315 grams to 465 as shown. Question I. Explain the increase in the reading on the balance. Your answer should include a reference to Newton's third law. Okay, so that's part I. Okay, let's write down a few arguments. So the water pushes up on the sphere, right? And this is the upthrust. Okay, by Newton's third law, the sphere pushes down, okay, on the water with an equal and opposite force. Okay, since the balance, okay, supports the container, okay, the extra force, the extra push, okay, adds to the balance, so the reading increases. Okay, so that's a good enough answer. Let's move on. Part 2, determine the mass of the sphere. Okay, so 0.465 minus 0.315 is equal to 0.150 kilograms. Okay, so that's the weight, that's the mass of the water displaced. Okay, so I mean, I'm using these numbers here. Okay, so this is the mass of displaced water. Okay, since by the way, this is question 2. Okay, so since the sphere is fully submerged, the volume of the water should be equal to the volume of the sphere, right? Now the volume, okay, is equal to the mass of water over the volume of water is equal to the mass of water over the density of water. So we can find the volume of the water in this fashion. So we get 1.5 times 10 to the negative 4 cubic meters. Okay, so the mass of the sphere now is equal to the density of the sphere times this volume that we calculated. So 1.5 times 10 to the negative 4 times 2000 yields 0.3 kilograms, which is the mass of the sphere. I hope this makes sense as an argument, okay? So let's move on to part 3, which is the last question. So the water was replaced with the same mass of oil and the experiment repeated. The density of the oil is less than the density of water. Explain the change in the reading on the balance when the sphere was suspended in oil. Okay, part 3, let's work down here. So if the sphere is fully submerged, okay, the displaced volume is the same, but the mass of oil is less than the mass of water, since the density of oil is less than the density of water. Okay, so we have less upthrust, okay, and less force pushing down. Okay, so let's use another clean page. So, oops, we don't need that. Okay, so the balance reading will increase, okay, but it will increase by less than 0.15 kilograms, which was the value we found earlier, okay. And this is the answer, okay, I guess. So to close it off, this is an off-season past paper walkthrough. I'm working on several other things that I plan for the channel. It's growing, but not as much as I would like. So any new subscriptions, any new subscribers, any help you can provide to the channel by any means possible are fully welcome. I always include a buy me a coffee link at the end of the videos, and hope they are useful and hope you are doing well this summer. So I'm gonna see you in the next video. So this was Unit 1A, okay, from October 2025. Bye.